I spend most of my time pottering around in our local backyard, Jupiter, Saturn, Enceladus, the moon, even sometimes diving down to Earth's core. But on occasion, I have thought about exoplanets, and I want to tell you today about some work not yet published, done with Yayati Chachan, who at the time he did this was an undergraduate at St. John's College in Cambridge. He's now a graduate student at Caltech. And it is motivated by this remarkable diagram. You have already seen examples of this diagram earlier in the meeting. This particular version of it is from Li Zheng at Harvard Smithsonian, and it shows radius as a function of mass for exoplanets. Earth and Venus are down there, bottom left. Uranus and Neptune are up there, top right. And this is an extraordinary data set. I would never have guessed as of a decade ago that we would be in a position to have such a diagram at this point. It's a mixture of data, but most of it, the fact that there are so many points on it is because of TTV, transit time variation data, which means, of course, that it's a biased set. It's looking at instances where you have multiple planets that are interacting with each other, and through that fact, you learn something about the masses. So typically, in this diagram, the radii are fairly well determined, although still with the caveat that you think you know enough about the central star. And the masses, as you can see, often have large error bars, and that's characteristic of TTV data, and it is a biased sample. But what I find remarkable about this diagram is, of course, the scatter. You can see on this diagram a number of lines that represent particular compositions, like giant cannonballs, 100% iron, through terrestrial type objects, up through ice balls, and then eventually hydrogen and helium. And there are assumptions that go into these lines, but it's quite clear that you cannot explain this scatter, for example, at around 3 Earth masses, just by saying that it's one of these condensed matter compositions. What you need, because of the objects sitting above any of these lines and the scatter, is something else. And that something else is a hydrogen atmosphere. Why hydrogen? That's simple. Hydrogen has low molecular weight, and with low molecular weight, you can have large scale height, and you can have many scale heights between the surface and the transit radius. Now, I need to remind you, many of you in the audience know this, but some of you may not. When we talk about the radius of an exoplanet that has an atmosphere, we're actually talking about very, very high in the atmosphere, like a millibar pressure. So you have to keep that in mind when you think about these numbers in those instances where it's a planet that hasn't been stripped of its atmosphere, but has a hydrogen atmosphere. The points are color-coded, by the way, in terms of the effective temperature, which is related to how far the planet is from the star. It's not particularly systematic, although in some instances you see evidence of a relationship to temperature, but I would hesitate at this point to say more than what I've emphasized so far, which is that you have a hydrogen atmosphere. So what's the implication of this diagram? The spread of radii for a given mass cannot be explained, in most cases, by the gross composition of 99% of the mass. Instead, it's explained by the other 1%. The fact that the radius is so large, the fact that it's puffed up, is explained by the fact that you have a hydrogen atmosphere, typically of order 1% or less in mass. And just to give you a feeling for numbers, if you have an atmosphere with a basal pressure of a kilobar, then that typically corresponds to only 1 part in 1,000 of the mass of the planet. By the way, you can do that calculation in your head if you're a planetary scientist. How? Because I know the pressure at the center of the Earth, and I know a kilobar is of order of 1 part in 1,000 of that pressure. It's really that simple. Now, at 1000 Kelvin, for example, and a 3 Earth mass planet, the pressure scale height is about 300 kilometers. The transit radius is out at about 10 to the minus 3 bars. So to go from 10 to the plus 3 to 10 to the minus 3 bars, that's 6 orders of magnitude. That's about 10 to 20 pressure scale heights. And that will already double the radius. So that's why many of these planets are popped up. It's really that simple. So the natural question to ask is, okay, the data tell us emphatically, without question, that a lot of these objects have a hydrogen atmosphere. It can't be lower, but it can't be some other constituent because it would be a much smaller scale height, and you can't explain the radii any other way. So there's really no doubt about that. So the question is, why do they often have a hydrogen atmosphere initially? Then we get to the question of why it might be retained. So here's the main point. If you build a planet, a terrestrial planet, a rocky planet, in the nebula from which the central star is forming, and do it quickly enough, and the data say about 3 million years, then of course the planet has formed in the presence of the hydrogen nebula, and there will be a hydrostatic solution that extends all the way from the surface of the super-Earth all the way out to the nebula. And you can do that calculation, straightforward calculation. Did it myself 40 years ago, other people have done it. And you can figure out how much atmosphere is grabbed by the planet. This, of course, is the very same idea that leads to the core accretion model for Jupiter. So this is very much tied to our understanding of how planets like Jupiter, Saturn, Uranus, Neptune form. But it's worth pointing out that the Earth didn't do this. So the Earth is already a little bit interesting and different. In the case of the Earth, we know from isotopic evidence that it took about 50 million years to form, more than an order of magnitude greater. At the time the Earth formed, even at the time that you started to build embryos that were, say, 20% the mass of the Earth, the atmosphere had gone. The nebula had gone, been stripped off, our sun sent back to the interstellar medium. So you can debate how common this is, but clearly there are many instances out there where the planets formed on that short time scale, and theorists have no trouble doing it in 3 million years. So you have the hydrostatic equilibrium all the way from the surface out to the nebula, and that will already give you of order this much, 0.1 to 1% by mass. And that atmosphere stays behind. Why? Because as it gets aggregated, it cools. It gets heated by isentropic compression, but then it radiates away, and so it becomes sub-isentropic relative to the nebula. And then when the nebula gets swept away, it stays because it has lower entropy. It's bound. This also presumably happened for Uranus and Neptune, although in that case, the masses are much more substantial. Now we come to a key point. Why is it surprising that atmosphere would stay around? Now, actually, this issue was already dealt with or discussed in quite some detail in connection with the Earth. The great Japanese astrophysicist Hayashi had a school of people back in the 70s and 80s, and they said the Earth itself had a huge hydrogen atmosphere and a surface temperature of 4,000 Kelvin. They got into trouble with the isotopes, and later people came to realize from isotopic evidence that the Earth took longer to form. So that's why the story doesn't work for the Earth. But they got rid of the atmosphere anyway, and how did they do it? They used UV from the sun and to some extent solar wind. And that is the story too for exoplanets, that you get escape from the planet. It's energy limited escape. There is admittedly some uncertainty in this process. The efficiency is typically about 10%. That is, the incoming XUV energy from the newly formed star is converted at 10% efficiency into doing gravitational work, taking the atmosphere back off. This is in, for example, the detailed models of Ruth Murray Clay, and other people have worked on it as well. In some cases, this can even lead to the atmosphere being completely stripped off the planet. But the fact remains that many of these objects, the ones I showed in my first slide of radius versus mass, are hard to explain. It seems that many of these bodies are retaining atmospheres when this kind of calculation would actually cause them to be stripped. So that's the puzzle that we're seeking to explain in our work. So here's our proposed solution. Our proposed solution goes as follows. The planet has a magma ocean. The magma ocean is in contact with the atmosphere in the first 3 million years. It grabs some of the gas. So the gas dissolves in the ocean, gets mixed by convection into the ocean to great depth. And even though the mole fraction of hydrogen in the ocean might be as low as 10 to the minus 4, because the magma ocean is massive, big fraction of the total mass of the planet, you can store inside the planet an amount of hydrogen that is larger than the amount that's in the atmosphere above. By the way, although it's not a particularly good analogy, to some extent the Earth does this with water. We think there's about as much water inside the Earth, in the rocks, as there is in the oceans of the Earth's surface. In that case, it's in solid rock. It comes out in volcanism, but it was in place there during the accretion process. So as the planet cools, this gas will come out and it will buffer the escape. That is, our picture is, we've got a planet, we've got an atmosphere, the atmosphere is escaping, but as the atmosphere escapes, the inside of the planet releases some of the hydrogen, buffers the escape, allows the hydrogen to come out, it degasses in a way that is modulated by the rate at which gas escapes to space. In order to build this picture, we have to think about 4 things. We have to first understand the initial state, the likelihood that you had a magma ocean in the first place. Second, the question of what the solubility of hydrogen in magma actually is, how it depends on both temperature and pressure. We have to convince ourselves that it actually gets mixed in there. We have to think about the physical process of mixing, and we have to do a thermal evolution model. So let me talk about each of those. First, on the question of the initial state. So here's a number that's worth remembering for Earth, our home planet. When the Earth forms, you've got this enormous gravitational energy release, dispersed material brought in to form a planet with a gravitational energy per unit mass of gm upon r, m is the mass, r is the radius. If you were to convert that to heat, it is the same as the latent heat of vaporization of rock. There is enough energy in the formation of the Earth to completely vaporize the Earth. It's useful to remember because that will remind you that there's a hell of a lot of energy in gravity. Now, of course, that's not what actually happens, but the point is that even if you only use 10% of that, even if you re-radiate 90% and keep 10, it's enough to melt the Earth. It's equivalent of 40,000 degrees temperature rise, and of course it scales as you go to bigger objects, as I've indicated here. So there's a hell of a lot of energy. So no problem melting. And here's the key point. If you have an atmosphere there as well, then that prevents the planet from efficiently cooling. And so in the absence of Maxwell demons, there is no way of avoiding a hot initial state. A hot initial state for a planet like this is mandatory. Not just possible, mandatory. And when I say hot, I mean the surface temperature of the magma ocean can easily be 4,000 Kelvin, just as it was in the Hayashi models of the 1970s. And of course, the surface of the ocean, the magma ocean, is set by the ability of the overlying atmosphere to convect the heat away. So let's talk about solubility of hydrogen in magma. This is something that petrologists, people who study the Earth, actually care about. not because hydrogen is a dominant volatile in the Earth, but on occasion it's there. It's there to a small extent in volcanic activity. The solubility satisfies this formula. X is the mole fraction of hydrogen in the magma. The linear behavior with pressure P is just Henry's law. It arises in fundamental physics from the fact that the hydrogen molecule goes into the magma as an H2 molecule. It does not dissociate. And the Arrhenius behavior is physically motivated. It comes from equating Gibbs energies, and the parameter T0 in that Arrhenius behavior is just telling you about the energy of insertion. That is, if I take a hydrogen molecule, stuff it into the magma, it has to push the ions away, and that's work that has to be done. And in thermal units, that's of order 5,000 Kelvin, although we don't know it very well. Our model is calibrated to the work of Mark Hirschman, but petrologists on Earth don't care about really high temperatures. Maybe they should, but they don't usually. And so they've only done measurements at a very narrow range of temperature. So we don't know for sure what T0 is, and so we treat it somewhat as an adjustable constant, but we think it's around about 5,000 Kelvin. And we choose the parameter P0, which is mostly entropic, mostly comes from the entropy of the ideal gas. So we know roughly what it is, but we calibrate the formula so that it fits Hirschman's data in the limited temperature and pressure range for which he has provided it. And here's the outcome of that calculation. So what you see in this diagram is the atmospheric mass relative to the dissolved mass. So 1 here, which is the top of this diagram, would be as much hydrogen in the atmosphere as there is inside the planet. And as you go down this axis to point 1, that would say there's 10 times as much inside the planet as there is in the atmosphere at time 0 before it evolves and cools and releases some of it. And it's plotted here as a function of planet mass, which enters into the problem in several ways, and also scaled in accordance with the initial surface temperature of the ocean. And we're using actually modest values, no problem getting to 4,000 Kelvin. And with 2 different choices of that parameter T0. But the key point here is that for super-Earths like 3, 4, 5 Earth masses in this range, we are often getting 3 or 5 times more gas stored inside the planet than is in the atmosphere. So that's the key idea in the story that I'm presenting. We come now to the tricky part, and this is the part where we can't be quite sure. How do you get the hydrogen in there in the first place? Okay, so you're making the planet, it's hot, it's got a magma ocean, and there's hydrogen sitting around in space. How did the hydrogen molecules decide to get inside the planet? Now, you might think that it diffuses through the interface. The magma ocean is vigorously convecting, the atmosphere is vigorously convecting, so there's a thin boundary layer through which the hydrogen can be driven by the Gibbs energy difference. Turns out when you do the calculation, that's not very efficient because the diffusivity of gas is very low compared to the diffusivity of heat. So that doesn't work very well. By the way, the corresponding problem for the Earth is to get CO2 across the atmosphere ocean interface, and that also is not, for the most part, done by diffusion. It's done by wave breaking, it's done by surf, it's done by various nonlinear processes, and we would invoke that as well, but we don't know how to quantify that. Certainly if you have impacts, you splash, that's great. Make surf, tsunamis, whatever. And bubbles can help. Bubbles are nice. Bubbles, which you can think of as boiling of the ocean, it's an excellent way. And that arises, of course, if you have an impact event that's compressing the hydrogen, and so you actually drive the hydrogen above the equilibrium value at the ocean. And then as that liquid comes back up, it develops bubbles, and the hydrogen gets released, but in the process, it's stirring the system. So you can debate this a bit. By the way, an interesting similarity arises here with a long-standing question in Earth science. Inside the Earth, we have neon, small amount of neon in the atmosphere, and there are 3 stable isotopes of neon, and on that basis, we can talk about how much of the Earth's neon came from the sun, the so-called solar neon. And people have debated endlessly whether this was incorporated in the embryos from which the Earth was formed, or whether it came in solid particles. In the case of Earth, it may actually have come in through solid particles, but part of the debate is the same things I'm talking about here. Can you actually get it into a magma ocean, which surely the Earth had? So, yes. So now let's talk about the thermal evolution. So here's the picture. Temperature, a function of depth. We have a radiative atmosphere, which extends well below optical depth unity. Why? Because the energy from the central star is much larger than the energy coming from the interior. And so if you work out the state of the atmosphere, you find that typically you have to reach an optical depth of more than 1,000 before it becomes convective. So this is an almost isothermal part of the atmosphere. Then you get the convective atmosphere, which sets the temperature at the surface. So this can all be calculated based on opacity, Friedman opacity tables, but it's basically pressure-induced opacity in hydrogen. So this is well known. And then you have the magma ocean. And then what happens is the system cools. So at a later time, the temperature in the magma ocean has gone down, so energy has come out. So this is what drives the convection of the atmosphere. So the atmosphere convection is driven by the difference between the blue line and the red line. And the location of the radiative convective boundary moves inwards. So all of that is in our model. I'm not going to show you a whole bunch of equations, but that's how we set up the model, and that's how we calculate what happens. And so here is an example of the results. What's shown here is mass loss rate off the top of the atmosphere over time. This is a log scale, so it's going from 1 million years on the left out to 1 billion years here, and the age of the Earth is over here. And what the key thing here is the difference between the blue and the green lines. The green line comes from the dissolved hydrogen, and it's much larger than the amount that was put there in the beginning. The fact that you have a flat line here is simply because in the model we're using, that most people use, the XUV flux is not changing much in the first 100 million years, and then drops off as a power law. So that's the shape of the curve. But the important thing of this message is the big difference between a model where you only lose gas from the atmosphere and a model where you can lose gas from the interior. And that's better explained here, where we show a model without any gas dissolved in the ocean, the red line, and the models where we have gas dissolved in the planet. And the key idea is that in this particular case for Earth mass body, the red line crashes. What does that mean? It means this planet got stripped in violation of the observations, at least for some of the objects, whereas if you put gas inside the planet, dissolve it in the planet, then it can survive. It can have an atmosphere out to the present day because of the buffering of the material that comes from the interior. So that's the story, and I want to finish, though, with some general comments about this. I think it's quite possible that these kinds of planets are the most common in the universe. Planets that have something like Earth composition, maybe some ice as well. Putting ice in the story is not going to change things that much, actually. So these are planets that have magma oceans. They have very hot surfaces. I think these are much more common than Earth-like planets. I think the label super Earth is a misnomer because it puts in people's minds the notion that we're looking at something that's like the Earth. And I think that's very unlikely. These are the most common kinds of planets. And of course, I labeled them super Earths, but they're also often labeled as mini Neptunes or whatever. So there's a gradation of possibilities there. So I think it's very common in the universe to have planets in which the surface temperature, and I define surface to be where you reach the condensed material, which in my case would be a magma ocean, is a lot hotter. So I think in general, planets are a lot hotter than people would guess by looking at the effect of temperature. I also think, and this is an old story of mine, that you can have distant planets with hydrogen greenhouses, including interstellar planets that have warm surfaces and can have oceans. I published this long ago in Nature. I'm not going to use the H word. I don't like the H word, but that's what I'm getting at. Even close-in planets with effective temperatures up to 1,000 Kelvin can sometimes retain atmospheres. I must confess that the story I've given you has a lot of variables in it. There are parameters we don't know that well. There are uncertainties about the particular sequence of events. So I'm hesitant to come up with a precise prediction, but I think we have a story that explains some aspects of the data I showed you at the beginning. And let me finish with an important comment. The inside matters. So when you think about planets, even if you're an atmosphere person, and even if you're looking at atmospheres, keep in mind the inside of the planet matters. And I'll stop there.